Okay, in our next unit, we're going to learn all about the circular functions. You may know them as sine and cosine and tangent and all of those. Before we get into that, these functions are all going to be derived from another function that we'll call w, and that's the wrapping function. The key to understanding the wrapping function is to get a good understanding from the get-go about the inputs and the outputs of the wrapping function. To just say it explicitly, the inputs of the wrapping function, it's the set of all real numbers, and the outputs is the set of points on the unit circle. The unit circle, you might remember from geometry, it's the circle whose equation is x squared plus y squared equals 1, and that's to say it's the circle centered at 0, 0 at the origin with a radius of 1. But putting it like that, it's not really clear what we're talking about when we say the wrapping function. So here's a couple of analogies that you can use to try to get your mind around exactly what this function is, because it is a little different than any function we've studied before. So one thing you can do is you can imagine that you have a piece of string, and that piece of string is sort of pinched down starting at this point 1, 0 on the x-axis. That's the point where we always start at. And you got that piece of string, and you stretch it out. It's some length long. It might be 1 unit or 2 units or 20 units long. And what you do with that piece of string is you just start to wrap it around this circle. So the input is going to be how long is the string. Maybe it's 2 units long or something like that. And the output is going to be what's the ordered pair x comma y on the unit circle where the string ran out, where it terminated. That's one way you can think about the wrapping function. The input is the length of string. The output is the ordered pair on the unit circle. Another way that I've always liked, another analogy that I've always liked to use is instead of a piece of string, because that's boring, who wants to think about string, you could instead imagine a little bug, so a little creepy crawly bug here. And this bug, I'll give him 6 legs, I guess it's some sort of insect. He's right here at the point 1, 0, that's where he starts. And you tell this little bug to start walking, and he just walks around the unit circle. Just starts walking around. And you tell him a certain length to go. You know, you go 4 units or something like that. And wherever he might stop, that's the output. The bug will say back to you, hey, I'm at this coordinate here. So the input is how far you tell the bug to go. He walks around the unit circle. The output is where he stops. That's the idea when we talk about the wrapping function. Okay, what we're going to do today is we're going to derive the coordinates of a number of wraps on the unit circle. And there's 16 different coordinates that we can see in this diagram that we're going to know. These are going to be committed to memory. We're going to learn how to derive these 16, so you'll have to know the derivations, and you'll have to know the actual ordered pairs that we get back out as well. Any other points other than these 16 going forward, we'd just figure those out with our calculator. But these 16 are going to be really helpful to do some quick arithmetic and things like that. So for starters, really all we need to know to get this investigated started is what's the circumference of the unit circle. And of course, circumference is 2 pi r. And as I mentioned before, it's the unit circle, which meant that its radius is 1. So my circumference is just 2 pi. All right. So remember what we do when we ask what's a wrap of 2 pi, like this first question right here, that means we're going to start at this coordinate, 1, 0. The little bug starts right there. And he's told to walk 2 pi units around the circle. Well, if the circumference of the circle is 2 pi, then he's going to come back exactly where he started. And that little bug's going to tell you his coordinate. That's the output. He'll say he's at 1, 0. That's easy enough. What if I asked a wrap of pi? Well, a wrap of pi won't take that little bug all the way around the circle, but it will take him halfway. So we can see that halfway around the circle is going to end up at this coordinate over here, and that's -1, 0. Halfway around the circle, it's helpful to remember that pi units is halfway around the circle. If we asked about a wrap of pi over 2, well, that means the little bug's going to go halfway to pi. So he's not going to make it halfway around the circle, but he'll make it halfway to halfway. which means a little bug will walk right up here to this point here. He'll be pi over 2 units away from wherever he started, and his coordinates instead of 1, 0 will be 0, 1. And the last one on the page here, what about a wrap of 3 pi over 2? You could think about it a couple ways. You could think of it as 3 turns of pi over 2, 1, 2, 3. You can think of it as 1.5 pi, which would just be half pi short of 2 pi, so coming back this way. Or you can think of it as pi over 2 more than pi. Either way, we're down here at this coordinate, and that is 0, -1. So those 4 are the first of the 16 that we will derive and that you'll have to commit to memory. And that's 2 pi, which is also known as 0. I put a comma there because you can say it either way, not because it's an ordered pair. Pi over 2, who has an ordered pair of 0, 1, pi, -1, 0, and 3 pi over 2, 0, -1. So those are the first 4. Of course, they're the easiest. We'll do the easy stuff first. On to the next page. Next, we'll find the coordinates of circular point. That's a wrap of pi over 4. So we'll just have to do a quick derivation. And the first thing that you want to notice here is that when we do a wrap of pi over 4, this point right here, well, that's going to be halfway to pi over 2. So it's going to be right smack in the middle of 1, 0 and 0, 1. And more to the point, it's going to be on the line y equals x. It has to be on that 45-degree line there because it's right in the middle. So if it's on the line y equals x, and it also must fit x squared plus y squared equals 1 because it's on the unit circle, I can just solve this system here by subbing in x for y. So I would then get x squared plus x squared equals 1. And x squared plus x squared is 2x squared. So I get 2x squared equals 1, which means x squared is a half. And that must mean that x is either plus or minus the square root of 1/2. Since I was imagining that this was in the first quadrant, I knew that this was in the first quadrant, I'll take the positive square root. So that tells me x is the square root of 1/2. Now, of course, that also means that y is the square root of 1/2 because x and y are the same. But I'm going to clean that up a little bit because most people don't call that coordinate root 1/2. Instead, they either call it 1 over root 2 because the square root of 1 is 1. Or for people who don't really like square roots in the denominators, they rationalize it by multiplying by root 2 over root 2, and they call it root 2 over 2. So this ordered pair right here, it has coordinates, let's give myself a little room here, root 2 over 2 for x, and the same exact coordinate for y, because, well, it's on the line y equals x. Root 2 over 2, root 2 over 2. All right. Now the nice thing about that is once I derive that one, these other points, these other wraps, wrap of 3 pi over 4, wrap of 5 pi over 4, wrap of 7 pi over 4, and as we'll soon see, wrap of really anything pi over 4, you can evaluate pretty quickly. You just have to identify the right quadrant. So if I think about the wrap of 3 pi over 4, that's a lot like a wrap of pi over 4, but it's like 3/4 pi's, like 1, 2, 3, right about here in the third quadrant. That's where 3 pi over 4 is located, in the second quadrant, excuse me. And 5 pi over 4, if I think about moving around the circle in the same units, 1 pi over 4, 2 pi over 4, which reduces 3 pi over 4, 4 pi over 4, which reduces 5 pi over 4. This is in quadrant 3. And 7 pi over 4, of course, would be 6 pi over 4, 7 pi over 4 here in quadrant 4. So I get all those for free after I derive a wrap of pi over 4. I just change the signs. So the little bug basically walks to a different point. Instead of saying root 2 over 2, root 2 over 2, he'll say negative root 2 over 2, positive root 2 over 2 for a wrap of 3 pi over 4. It's negative x because it's in quadrant 2. And 5 pi over 4, both the x and the y are negative because it's in quadrant 3. And for the last one, 7 pi over 4, only the y is negative. That's a weird equal sign because it's in quadrant 4. That's not too bad. Okay, so far we've derived 8 special points on our unit circle. If the bug walked any of these distances, we'd be able to say what the coordinate was. We only have 8 more to go. And these are all going to come from really one derivation. Okay, so the next thing we'll figure out is the coordinates of a wrap of pi over 3. And the way this derivation is going to go, just to save a little time, a few facts that we know. What we're going to do is we're going to take this upper semicircle, which would be an arc of length pi, and divide it into thirds. So you can see these 3 little pieces I've created here and the 3 segments that go along with them. So you notice that a wrap of pi over 3 and a wrap of 2 pi over 3, so a third of the way to pi and 2/3 of the way to pi, they're symmetric to the y-axis. So if I give pi over 3 coordinates a, b, then 2 pi over 3 would have to have very similar coordinates, just with a negative a and a b. Well, that means that the segment joining negative AB and positive AB, this little segment right here, this has to have a distance equal to 2a. And for right now, I'm just going to call that D1. Likewise, the segment joining AB and 1, 0 will also have to have a distance of 2a, and I'll call that one for right now D2. So those distances have to be equal, and the rest of the derivations is going to fall in line from the distance formula. So D1 equals D2 is where it'll start. D1 I know to be 2a. You can just see that because we're moving horizontally from negative a to positive a. D2, meanwhile, will have a distance that I can describe with the distance formula. So it'll be the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates squared. So that would look like this. A minus 1 squared plus b minus 0 squared. All right, and then what I'm going to do first is I'm going to get rid of that nasty square root. Square the left side and you get 4a squared. Square the right side and you'll get rid of the square root. You'll get a minus 1 squared, and I'm going to just write that as b squared there instead of b minus 0 squared. In the next step, I'll expand a minus 1 squared. 4a squared equals a squared minus 2a plus 1 plus b squared. And then here's the step where it's very, very tempting to take that a squared and bring it over there and combine it with the 4a squared. But if you do that, you're going to screw it up and you're never going to figure out where you went wrong. The key is, at this step, is to pay attention to the fact that you've got an a squared plus a b squared on the right-hand side, and this is the unit circle, x squared plus y squared. Well, a is the x-coordinate and b is the y-coordinate, so a squared plus b squared has to be equal to 1. That's going to be true because we're on the unit circle. AB is a coordinate on the unit circle. So a squared plus b squared is 1, plus another 1 makes 2. So color back here. It would be 4a squared equals 2 minus 2a. And look at that, we got a quadratic to solve. I'm just going to bring it up here to finish it off. It would be 4a squared plus 2a minus 2. If we group everything on the same side, that would equal 0. Divide those even numbers out, it would be 2a squared plus a minus 1 equals 0. That looks like it has a chance to factor. Let's try it. 2a and a, and it's going to be 1 and negative 1. I think with the negative 1 here and the positive 1 here. Let's check that. Does it work? Does it work? Does it work? I think it does. That means either a equals 1/2 or